Let's take a look at some airfoils. So an airfoil is any surface that provides aerodynamic force through interaction with moving air. So that'd be a good thing to add to your notes in your engineering notebook. I believe we've all probably done this arm out the window thing. Coolest thing ever. There is your airfoil, and we have moving air, and then it's causing it to lift up. So we've all experienced that. Super fun. Forces in flight. What forces act on an aircraft to ensure flight? You automatically have the weight of the aircraft. Lift is a force that is created by the effect of airflow as it passes over and under the wing. So remember from our discussion on what creates lift, it's going over the wing and it's going under the wing, because as it goes over, Coanda effect holds it to the top of the wing and then pulls the air down. So what occurs when lift and weight are equal? Well, it's in equilibrium, so nothing happens. You're not climbing, you're not descending, you're just at level flight. So something happens, you're at level flight. So lift is created by airfoils. They have a curved shape to direct airflow. We've taken a look at this briefly. Here are a few examples of some different types of airfoils. So again, air movement over and under the aircraft wing create pressure differences. Depending on which type of airfoil you have, you're going to get a greater pressure difference, or maybe even a greater downwash than you would on a different style of airfoil. So that's one thing that we're going to take a look at when you decide which airfoil design you want to create. So let's look at lift. It's air movement over and under an aircraft again. And the lift force is always opposite to the weight. And lift force is also used to turn aircraft when the aircraft rolls, because your ailerons produce different amounts of lift. As your ailerons move in either direction, remember at the outsides of the wings, then they're creating different lift. And if you have greater lift on the left side, then you're going to end up rolling to the right. If you have greater lift on the right side, then you roll to the left. So please draw this cross section of the airfoil, and that's what we're going to be taking a look at. Again, you can see it's a cross section from this display over here. So if your direction of flight is forward here in this exact direction, and air is opposing it in this way, then we're going to get a little bit of lift. So let's take a look at the different components. So the first thing that you should label down is leading edge. It's the first point of contact between the airfoil and the moving air. So if you need to pause this as you're writing down, please do so. The second point is the trailing edge. It's the point of last contact between the upper and lower surface. So way down here is your trailing edge. Your chord line is what is drawn in between. So from leading edge to trailing edge, that's your chord line. The camber, or camber, depending on which pronunciation you go with, is a curve of the upper and lower surfaces of the airfoil, and it determines the air velocity on the upper and lower wing surface. So we have an upper camber right here, and the lower one is not quite as curved. It's a little bit smoother. So this is an asymmetric. It is not symmetric, so it's asymmetric. And then your chord line is in the middle. So please label upper and lower camber, and then make sure your chord line is in there. And your mean camber line is the average distance between the upper and the lower surface. So that line may not be the same as a chord line. In which case is it the same as a chord line? Symmetric, very good. If they're symmetric, then the mean camber line is exactly at the same place as the chord, or as the chord line. We'll look at this picture. Those would be in the same place if it's symmetric. So a high lift device, flaps will increase the camber equally on both wings, and they increase lift and increase drag at slower speeds for takeoff and landing. So if the flaps are retracted, if they're not being pulled down, so in a normal situation, then you have this nice smooth flow here. But if they're extended, then it drops down. So now what you can see is going to happen is the air is going to travel along here and then be pulled slightly down, so you're going to get a greater downwash. You're also going to get a greater deflection with the flaps down here. So it should provide more lift. It provides significantly more drag. So that also helps to slow the plane down and give it more lift at the same time. Great for takeoff and landing. For takeoff, you're pulling yourself through the air with high thrust, so it's not an issue for takeoff, but it does give you more lift. For landing, when you want to slow down, it's great. So we have increased camber here. And then here is our new chord line from leading edge to trailing edge. Angle of attack is the angle between the chord line and the direction of the wind. So a chord line is here. the relative wind is going this way, which means the plane is going straight forward. So the wing is kind of at a little slight angle here. And as we talked a little bit about with lift, hopefully, is that as this plane is maybe not quite going fast enough, it's the wing might be tilted down, or that might just be how the wing is attached. And so we have a slight angle of attack right here. You don't necessarily have to have zero angle of attack at all times. It kind of just depends on how the wings are attached and how the wings are designed to give you lift. So the maximum angle of attack is where airflow separates, and that is called the critical angle of attack, and that's where stall occurs. So again, as hopefully we looked at when we did our review on lift and how wings provide lift, a lot of us noted that Coanda effect pulls the air down, but if we're going too fast, the Coanda effect is not strong enough to overcome the steep angle, and the air actually just travels over the top, which creates all these vortices. So we lose the lift on the top, we still get lift on the bottom, but it's not nearly enough, and that's why we call it a stall. Alright, so a little review. As I click through these, see if you can answer each one of them without looking at your notes, and we'll see how you do. So this first piece, as this arrow is pointing here, what is it? Alright, how about this top one here? And this back one here. This gray line that's going right through the middle here, not the dotted white one. Alright, now this lower edge. Good. And this triangular section here represents what? Angle of attack, right on. And our last one is this dotted line. So what does that represent? So I hope you did well on that. If not, what I'd suggest you do is go back and quiz yourself again and see if you can learn these terms. It's important that you are able to distinguish these, especially when you make your own airfoil. So using flaps for lift and drag, this is the most efficient, and if we retract them out, then you get an increased wing area, and that's what's great for takeoff and initial climbs when they're retracted out. When they're retracted out and down, that's when we get drag to slow us down and even more lift. So there are a couple different scenarios for the flaps, and that hopefully answers the difference between flap retraction for takeoff and landing. And then last is lifting up this flap here. It's one extra piece. So if you're flying in an airplane, if you looked out the windows on landing, you may have noticed these go up. Usually that's when you're on the runway. And this is used to deflect air up, and it really removes all lift altogether and slows the aircraft down at the same time.